Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to Optimization in Civil Engineering. In the last class, we discussed about the multivariable optimization with equality constraint, and we attempted to solve the problem using direct substitution method. The method was quite effective and useful to solve simple problems with one or two equality constraints. And if you look into the problems which we had solved, those problems mostly had the equality constraints which are linear. You can imagine a problem with more than 2 or 3 equality constraints, and those constraints are nonlinear. In that case, direct substitution would result in a very complex equation for the objective function, which might be difficult to solve using the method we had discussed earlier. Apart from that, we also need to understand the variables which we want to substitute by solving the equality constraint. Since we have more number of variables than the equality constraint, it depends on us the variable which we want to choose at the time of solving and consider them as an independent variable, so that we do not replace those variables, and identify the variables which can be replaced in the objective function, which we are going to indicate as dependent variable. Today we are going to discuss about another method where we can look into the constraint variations within the equality constraint equations and try to identify the independent and the dependent variable in a much simpler way, which could be useful and effective to solve the multivariable optimization problem. As we had said in our last class, that an objective function for a multivariable optimization problem can be either minimized or maximized for a set of constraints. In this case, the constraints are of equality nature and indicated as HK, where the total number of constraints are of M, and the variables are represented by n-dimensional array. Now we had also indicated that if the number of constraints is less than or equal to the number of variables, then we can solve for the n minus m variables. However, if the number of constraints are more than the number of variables, then the problem is overdefined and it is difficult to have solution. And we had also indicated that the various solution methods that we are going to discuss in this class are going to be direct substitution method, constraint variation method, and Lagrange multipliers method. We had already discussed the direct substitution method in our last class. Today we are going to discuss about the constraint variation method. Once we obtain the optimum variable value for a particular objective function, we know that the first order derivative of the objective function at that point is going to be 0, and this is the necessary conditions for the optimization problem. And since in this case we also have equality constraint, the point which satisfies the optimum point, the point which satisfies the optimality is also going to satisfy the constraints. Hence, we are indicating that the constraints at that particular point is going to be 0. So let's look into the other situation. If we obtain a set of points or the optimal points that satisfy the unconstrained objective function's necessary condition but do not satisfy the constraint, then that particular points cannot be considered as an optimal point. Rather, we have to find a set of points that satisfies the constraint and then check the objective function whether the objective function is minimum at one of the points we have selected. So in that case, we are saying that x cap is such point that satisfies the constraint which is equal to 0, and for this point we have to see the function value whether it is minimum, or maximum or a saddle point. Now with this basic theory, we'll be looking into the problem in depth. As we had indicated earlier that as per the necessary condition, the first order derivative of our objective function is going to be 0. So if it is 0, which is this, then any variation about the point where the first order derivative of my objective function is 0 is also going to be admissible, and the new point indicating the variations should also lie within the equality constraints. So in this case, our equality constraint hk and the point variation which is represented as x1 star plus dx1, x2 star plus dx2, these points should satisfy the equality constraint, hence it is expected to be 0 for all the equality constraint we have for the particular objective function. Now this objective function, if we do a Taylor series expansion, then we can write it as hk, the point x star, and the first order derivative with respect to each of the variable, the partial derivative, and this is going to be equal to 0. Now we already know for a particular point where we have obtained the optimum function value, the constraint is equal to 0 for the equality constraint. Hence we are indicating this here, and we also know this expression is actually the first order derivative of the constraint Hk. So if we look into the Taylor series expansion again, then we can clearly say that the left hand side part, this is equal to the first order derivative of the constraint. The right hand side, the first term is equal to 0, and the remaining term stays here, which is supposed to be equal to 0. We are going to explain this or look into this generic form and try to develop our theory for the constraint variation. As we had said that the first order derivative now can be written as this, which is equal to 0 in a generic form at a point x star. Then we can say if we have only one constraint and two variables, this equation can be easily written as this way. And here this is equal to 0. So we can express this particular equation in such a way that dx2 becomes of this value. Now here you will see that we can say that this is independent and this is dependent. So which means our x1 is independent and x2 is dependent. So if we replace this value in the first order derivative of the objective function, we can write the first order derivative of our objective function as this, where after replacement dx2 it is going to be of this. Now this one, if we further look into and represent it in a matrix format, we can write it in this way, where this matrix is equal to 0. And here, as I had indicated, x1 is my independent variable, and x2 is my dependent variable. So if we can write this for the two variables and one constraint, we can expand it for the m constraints and n variable in a following way. Here you will see that the first column represents the independent variable, which I had marked it here, and rest of the columns are representing the dependent variable, which I had indicated it here as well. So this matrix can be represented in a Jacobian form of this way, and this, as we had said, it is going to be 0, so this Jacobian is going to be 0. Here we, as I said, the first column is representing the independent variable. So in this case, the independent variable, which is in excess of m, because we have solved for m number of constraints, so anything which are not solved for the m constraints above m but up to the n are going to be the independent. So we are indicating it as m plus 1, m plus 2 till n. Hence, if you are looking into the matrix, we are going to generate m plus 1 to n number of matrix, which is going to be like this. And that is why we are saying it is going to yield n minus m equations. So when it is yielding n minus m equations, and which is supposed to be equal to 0, we need to understand the requirements of this Jacobian. Now let us quickly look into this matrix in details. As I had said, the first column represent my independent variables and all the other columns represent my dependent variables. Now we said this particular matrix is equal to, we need to ensure that this portion of the matrix is not 0. If this portion becomes 0, then we cannot say for sure that this portion is going to be 0 or non-zero. Hence, in that case, we can say, even though it is satisfying the condition, but we are not sure about our independent variable. So, as I had said, this Jacobian, which is representing this part, is not going to be 0, and if we look into this part of the Jacobian, we can clearly say it represents the first order derivative of the dependent variables for the constraint functions, or we can say these are the dependent variables in the constraints. So this can be written as the Jacobian. If we say that this Jacobian is equal to 0, implies that the Jacobian for the dependent variable for the constraints should not be 0. And this is important to find the m dependent variable that satisfies this condition. So we can have many combinations of the m dependent variable, but we have to find the combination which is going to satisfy this particular condition when the Jacobian of those dependent variable in the constraint function is not going to be equal to 0. Let us look into one of the examples to understand this process better. Here in this example, we have the objective function which we want to minimize, and we have two constraints, and these are the two equality constraints. So if you are trying to solve, here we have the number of variables as equal to 4 and the number of constraints equal to 2. So first we have to assume which are the variable going to be the independent variables. In the first, we assume that the x3 and x4 are going to be the independent variables, and if we consider these two variables as independent, we can write the Jacobian of the dependent variable as this, and if we find the values of these partial derivatives and solve the and find the determinant, we'll find that the determinant is going to be 0. So it is actually defying the requirement of the Jacobian of the dependent variable, and hence we cannot select x3 and x4 as independent variable. We have to choose some other variable as an independent variable. Hence we are saying that x1 and x2 cannot be the dependent variable for this problem. So in the next step, we are choosing x2 and x4 as the new independent variable. And now my Jacobian of the dependent variable is going to be this, which is going to yield a determinant of 2, and which is actually not 0. So we can definitely consider x1 and x2 as the dependent variable and x2 and x4 as the independent variables. So once we select our dependent and independent variable, we need to check the necessary condition. So as per the necessary condition, we said that for each independent variable we'll have one matrix. In this case we had two independent variable, which is x2 and x4. So we have two matrix, one and the two second matrix. So these two matrix, if we try to solve, then we are going to get this equation, which we need to make it equal to 0, and for this one we want to make it equal to 0. So we have two equations, and from these two equations we want to find out our optimum point. And if we try to find the optimum point, we'll see that x1 is equal to half of x2, x3 is equal to 2 times x4 minus 7x1, which is also going to be equal to 2 times x4 minus 7 by 2 x2. If we replace the value of x1 and x3 in the constraint equation, then we can represent the constraint equations in the form of x2 and x4, which is shown here, and these constraints are equal to, the values are going to be 10 and 15, and if we solve these two constraints, we can get the values of x1, x2, x3 and x4, where we can expect the function value is going to be optimum or saddle point, or we may need to further investigate. That is going to be decided based on the sufficiency condition, and for this we'll look into the sufficiency condition. Now, as we had said that the equality constraint helped us to eliminate the m variables and make the objective function of n minus m variable. So now let's look into the objective function. If we want to do the Taylor series expansion of the objective function above the optimum point which we obtained at x star, then we can write the objective function as function of x star plus dx, which is equivalent to the function of x star, and we have only m plus 1 to n variables, so we can write this is going to be our first order derivative and this is going to be the second order derivative. We are neglecting the higher order terms, so which we can easily write in this format. Here is one interesting thing, that at the optimum point we know the slope or the first order derivative is equal to 0. Then we can clearly see that the function value in the neighborhood of x star, the optimum point, will depend on the function value at the optimum point and the second order derivative. So in the neighborhood of the optimum point, if we find that the function value is greater than the function value at the optimum point, then we know that we have the function value as minimum. So if we can write this as if this is greater than fx, then we know that x star represent the minimum point. It is possible only when this is going to be positive. Then only we can make the left hand side and right hand side equal. So exactly this is what happens when we say that the second order derivative is positive definite, then we have reached a minimum point. On the contrary, if we find that instead of fx star plus dx is greater than fx, this function, if it is less, then this has to be negative, which is when we say that the second order derivative is negative definite and we have reached to a maximum point. So we need to investigate the second order derivative, which is represented here. Let us look into this second order derivative, and in the sufficiency condition, if we want to represent the second order derivative, we can write the second order derivative from the previous equation in this form, which can be represented as a matrix of this nature. And here we have to do the second order derivative of this nature. This is going to be difficult, particularly if the number of constraints quite increases. However, this particular problem is going to process is going to lead the path for a much easier process of Lagrange multipliers. We'll discuss about the Lagrange multiplier in the coming class. So today we learned about how to use the variations of the decision variable in the constraints to identify the dependent and independent variables, so that we can replace the dependent variables in the main equation and use the Jacobian to solve the optimization problem. While solving the optimization problem, particularly in the necessary condition, we could easily identify the points where we may potentially obtain the optimum solution. However, to check whether the solution is going to be optimum, that is minimum or maximum, or it could be a saddle point, or we need to do further investigation by looking into the higher order derivatives, we need to look into the sufficiency conditions. While investigating the sufficiency condition, we realize that the partial derivatives which we need to evaluate can become quite difficult, particularly when the number of constants are going to increase and may be more than 3. In this situation, we need to look into some other process which depends on the constraint variation, however with some modification. So in the next class, we are going to look into the Lagrange multipliers, which is going to use these sufficiency conditions we discussed in today's class to further modify and to come up with the process which can be used to identify the optimum solution. So we'll meet again in the next class. Until then, thank you.